Chemical equations. Did you ever hear the rhyme, beans, beans, magical fruit, the more you eat, the more you toot? Well, that's a good example of a chemical reaction where you really don't want to be around to witness it. So chemical equations are going to allow us to do just that, to make predictions and to be able to understand some chemical processes without even being there. And for example, with tooting, right, if you have some undigested bean skins, it creates these products. And pretty much all of them, you can't smell it. It's the sulfur compound that really makes toots stink. Balancing chemical equations. On the left-hand side, we always have reactants. The right-hand side, what's being produced, the products. Is the below chemical reaction balanced? This is one way of looking at a chemical reaction. The reactants and the products, they're all just using chemical models. But the idea here, and what you should visualize, is that we cannot create any new atoms. We have to have the same number of atoms of each element on both sides of the reaction. So we have, you can see you have one black sphere on both sides. You have, 4 of these red spheres. And there's 4 red spheres on the other side. There's 4 of those blue atoms, and there's 4 blue atoms. So there's the same number of elements on both sides. So yes, it is balanced. So if the black, red, and blue represents carbon, oxygen, and hydrogen respectively, write a balanced chemical equation. So that means we have a carbon, right, for this guy. We're going to have a carbon, and the blue are hydrogen atoms. So we have 4 of them. That's methane. And then we have these red spheres, and red is oxygen. So now we have these oxygen molecules, but we have 2 of them. So we have 1 methane molecule and 2 oxygen molecules produce, okay, we've got an OCO. Now that's the same as carbon dioxide. It's a more common way of writing it. Plus, we have an O and these H's. We've got 2 of those molecules. Water, right? 2 H2Os. So this is the more typical way that we're going to see chemical equations and chemical reactions. We know an equation is balanced when we have the same number of atoms of each element on each side of the chemical equation, reactants and products. So here's some helpful guides here. This is going to seem kind of random in balancing these chemical equations, but that's just how it is right now, so just hang in there. Balance last any element that occurs by itself somewhere in the chemical equation. So let's say we have a chemical equation, and somewhere in here we have O2. So that's an element all by itself. It's just oxygen, so balance it last, right? Or let's say you had somewhere Fe, iron, all by itself. Balance it last, okay? Whenever you have an element on its own, just balance it last. Combustion reactions always produce what and what? Water vapor and carbon dioxide. Okay, know that. That'll help you get through some homework questions. So let's see if we can balance some chemical equations. Now, when you're trying to get the same number of atoms of each element on both sides, the only thing you can change and have control over is the number out front. Okay, those numbers out front are called the stoichiometric coefficients. Those are the only numbers that you can change. You cannot change subscripts. These are fixed. Do not change. You can't change them. Otherwise, you'd be changing the compound. You can't do that. So let's start out here. Remember this rule number 1. Any element that occurs by itself, balance it last. Iodine is all by itself, so do this last. You don't have to, but I'm just saying life will be easier. So let's try, what do you want to try? Let's just try the sodiums. Okay, we've got 2 sodiums on this side. On this side, we have how many? 2 and 1, we have 3 sodiums. So what can you do to make them the same? Well, we could put a 2 in front of this one. That would make it 4. And then we could maybe put a 2 in front of this one. Then we have 2, and 2 is 4. So that would work. Then we have 4 sodiums on both sides, right? So if we have sodiums are good, how about the sulfurs? How about the sulfur atoms? The sulfurs, I have 4 sulfur atoms here, and I've got 4 sulfur atoms there. Hey, good deal. How about the oxygens? On this side, I have 2 times 3. I have 6 O's. And on this side, I've got 6 oxygens. So they're done. So the last element are the iodines. We have 2 iodines on this side, and we have 2 iodines over here. It's good. So when a number is not written, that means it's a 1. When a number is not written in the front, that means the stoichiometric coefficient is a 1. So very often they don't write them, they just leave it. So there's our balanced chemical equation. 2 moles of sodium thiosulfate plus 1 mole of iodine produces 2 moles of sodium iodide and 1 mole of sodium, what would that be? S406, whatever element, pi-atomic ion that is. Okay, so go ahead and try these and see if you get the same answer as I do. Okay, so let's do the carbons first. Why not? 6 carbons, 6 carbons. So I'll do this one last. So that means you have to do hydrogen next. So I'd have 6 hydrogens. I need to have a 3 there. Okay, now on this side, 6 times 2 is 12 plus 3. I have 15 oxygens. On this side, I need 15 oxygens. So there's a trick to doing this that makes life a lot easier. Let's cheat. These stoichiometric coefficients have to be whole numbers, but let's just cheat for now. If I take 15 halves times 2, I've got 15 oxygens. I'm done. This works. It's just that it's not the correct convention. So what do you got to do to make this in the correct convention? You cannot have, they don't want fractions as stoichiometric coefficients. So let's just change those. So let's just change those coefficients. Since it's nice and balanced, whatever you do to one side, you have to do it to the other side. So let's multiply through by what number? Multiply through by 2. This would be a 2. This would become a 15, 12, and a 6. Next one. 1 phosphorus, 1 phosphorus. 5 chlorines, 5 chlorines. 5 hydrogens, and 3 would be 8 hydrogens. Over here I need 8 hydrogens, so if I put a 4 there, I would have 8 hydrogens. How about the oxygens now? 4 oxygens, 4 oxygens. Done. Number 4, we don't have any elements by themselves, so just work with what we have here. Let's start with the nitrogens, I guess, right? This 2 means I have 2 of these ammonium groups. So I actually have 2 nitrogens. I actually have 2 nitrogen atoms. So over here, I need 2 nitrogen atoms. So let's put a 2 in front of that. So then I would have 2 nitrogens. Okay. It looks here like I've got a sulfur and a sulfur. Sulfurs look good. 2 times 4, 8 hydrogens. 6, 8 hydrogens. That's good. What about the oxygens? 4 and 1 is 5. 4 and 1 is 5. Hey, it's balanced. Nice. Number 5. I'm going to start with the hydrogens. I got 2 hydrogens. 2 hydrogens. Now I've got 3 nitrogens. 3 nitrogens. 3 times 2 is 6 and 1 is 7. 7. Good. So So the idea here is just try to balance these chemical equations so that you have the same number of atoms of each element on both sides. And it's usually easiest if you balance last an element that's all by itself.